Welcome to the deep dive. Today, we're cracking open the essential playbook for anyone operating in a clinical laboratory. We're going right to the heart of how analysts make real evidence-based decisions when they're, adopting new technology. Every time a new analyzer rolls in or you change a batch of reagent, the gut reaction question is always, are the results accurate? And that's a good starting point. But our sources, the foundational literature of lab quality, they say that's really only half the story. The really powerful question is the error inherent in this method within acceptable clinical limits?
That is such a critical shift in thinking, moving from just accuracy to acceptable limits. And the metric that drives that whole assessment is total allowable error, or T.
T?
Exactly. It's the defined tolerance limit that tells you objectively if a new method is good enough to keep your patient safe. It transforms a kind of subjective accuracy check into a really robust scientific evaluation.
So that's our mission for this deep dive. We're going to unpack T, explain why it's a much better evaluation tool, and most importantly, we're going to walk through the 4 practical steps you need to use it. This is all about turning that high-level theory into what you actually do day-to-day in the lab. So let's start with the big why. Why do we even need T? Why can't we just rely on our standard accuracy checks?
It's because simple accuracy, it only looks at one piece of the puzzle.
Okay.
Accuracy is generally concerned with systematic error, which we call bias,
right?
How far off your average measurement is from the true correct value. But in the real world, error comes in 2 flavors, and T forces you to account for both.
And the second flavor is?
The second flavor is random error. We measure that using the standard deviation, or SDP.
Oh, okay.
The random error is it's the imprecision, the inevitable scatter you see in results from all sorts of tiny variations.
Like temperature or pipetting.
Exactly. And if you only look at bias, you might approve a method that's correct on average, but it's so imprecise that it gives dangerously wrong results to individual patients. T demands you look at both the bias and the SD.
That makes perfect sense. So T is like creating a safety perimeter around the true value. Now, before we get into the steps, the sources we reviewed mentioned 2 big external standards for defining that perimeter, CLIA and Ricos. Can you just quickly place those for us?
Sure. They're both very common sources for setting that initial T value. CLIA stands for the Clinical Laboratory Improvement Amendments.
That's the U.S. standard.
Yes. It sets quality standards for all human testing in the United States. Ricos is a system used more internationally, especially in Europe, and it's based on desirable biological variation. They both provide these consensus limits that labs really should adopt.
Okay, great. With those benchmarks in mind, let's get practical. Let's walk through those 4 steps. Step 1 is choosing the target.
Precisely. Step 1. Choose the appropriate T. Before you even run a single sample, you have to define what's acceptable.
You set the goalposts first.
You have to. And ideally, use sources from an external body like CLIA or Ricos, because those limits have a strong scientific backing tied to clinical outcomes.
But what if you can't? I imagine that's a real challenge for smaller labs.
It is. And in those cases, the lab has to define and justify its own internal limits. The key thing here is that an internal T has to be defensible. You can't just pick a number.
So it has to be based on something solid.
Right. On the medical significance of the test or data from a previous high-quality method. But external limits are always the strongest defense in an audit.
Okay, so that sets our goalpost. Now we have to collect the evidence. How do we approach step 2? Collect verification data. What does that actually look like?
It means you're collecting enough data points to be statistically significant. This isn't just one quick test. You're trying to capture the full picture of how that method performs.
To get those 2 key stats we talked about.
Exactly. Bias and SD.
So for bias, you're comparing your new method against some kind of gold standard.
A highly stable reference material, or a validated reference method, yes. That difference between your average and the true value, that's your bias, your systematic error.
And the SD is just the spread of your own results.
It's the scatter around your average. You're looking for high precision, which means a low SD.
I remember the source material had a really practical tip for labs that maybe don't have access to expensive reference materials.
Yes, and this is key for managing resources.
Yeah.
If you don't have that ideal reference material, you can use stable, well-characterized patient samples. The point is to use something that is stable and truly represents what you'll be testing every single day.
Great. So now for the magic moment where we combine systematic and random error into one number. Step 3, calculate the total error, or TE. Let's talk about the formula, and specifically this mysterious Z factor.
Right. So the formula is designed to combine the bias with a statistically relevant multiple of the standard deviation. The calculation is TE equals bias plus Z DSD.
Total error equals bias plus Z times SD. So what is that Z? Why isn't it just bias plus SD?
That's the crucial question. It's because we can't just accept a result based on average performance.
Right.
We're making decisions that can be life or death. So we need very high confidence that a measurement will be reliable nearly all the time. The Z factor is what builds that statistical confidence into the result.
And there's a specific number we need to use.
For clinical quality, yes. We mandate 95% confidence. And to get that level of confidence, the Z value must be set at Z equals 1.96.
1.96.
1.96. That number is statistically derived to ensure that there's a 95% probability that the error you see in the future won't exceed the TE you've calculated.
So using 1.96 is basically a mathematical guarantee. It means only 5% of future measurements might fall outside that total error limit we calculate.
Exactly. It's a statement about your tolerance for risk.
Yeah.
Using Z1 would only give you about 68% confidence, and for patient results, it's an unacceptable level of risk.
Yeah.
The 1.96 makes the TE a robust predictor of real-world performance.
That really clarifies the stakes. Okay, so now we have our total error, our TE number. Now for the moment of truth. Step 4, compare TE to T.
This is where it all comes together. The rule is simple. If your calculated total error, the error you actually observed, is less than or equal to your total allowable error, the limit you set back in step 1, then the method passes.
TE is less than or equal to T.
You're good to go. But if your calculated TE is greater than your T, the method fails verification. Full stop.
And then you have to go back to the drawing board.
You either investigate the source of the error, optimize the method and try again, or you just reject that method or region entirely. It's the objective gatekeeper for quality.
Let's make this really concrete. The sources gave a great example of evaluating a new glucose reagent. This should bring all 4 steps together. Okay, so let's say the lab used CLIA to set its T. For glucose, that's 10%.
Right, that's our goalpost from step 1.
And after running their samples in step 2, they found a bias of 3% and an SD of 2%.
Okay, so we just plug those numbers into our formula. TE equals bias plus Z SSD.
Mm-hmm.
And we absolutely have to use Z equals 1.96 for that 95% confidence.
So the calculation is TE equals 3 plus 1.96 times 2.
Exactly. And 1.96 times 2 is 3.92.
So you add that to the 3% bias, and our total error, our TE, is 6.92%.
6.92%.
And now we compare that observed error, 6.92%, against our acceptable limit of 10%.
And the conclusion is clear. It's acceptable. 6.92% is well within the 10% limit.
So the method is verified.
It's verified, and you have the proof. You've shown that the combination of its systematic error and its predicted random variation falls within a clinically safe range. The power of this is that you have quantified your risk before you release a single patient result.
That's a much safer position than just saying, it seems accurate.
A fundamentally safer and more defensible position, yes.
So moving beyond just the math, the sources also really stress that this whole process has to be part of a rigorous quality system. What are the key administrative requirements?
Documentation, and more documentation. Every lab must meticulously document the T-limit they chose, the raw data from step 2, the full calculation from step 3, and of course the final decision from step 4. If it's not written down in the eyes of an auditor, right, it never happened.
And there was also a point about collaborative evaluation, which seems especially important for, say, a large hospital network.
Absolutely. Quality shouldn't be a solo effort. Labs are really encouraged to share their verification findings with their team with other labs in their network. It helps spread best practices and can help you spot systemic issues that one person might miss.
So this has been a really practical deep dive. Let's quickly recap the key takeaways for everyone listening. We've established that T is really the supreme metric for lab quality. It's better than simple accuracy because it forces you to combine systematic error, the bias, with random error, the SD.
And that the statistical guardrail for all of this is that Z factor.
That crucial Z factor of 1.96, which gives you that non-negotiable 95% confidence level you need for clinical work.
And, if we circle all the way back to that very first step, choosing your T, the source materials bring up a challenge that never really goes away. There's this tension between using those externally mandated limits, like from CLIA, and having to define your own internal ones, maybe because resources are scarce. Mm-hmm. And this brings up a final question for you to think about. When you are operating with limited resources and you have to set an internal T threshold, how does your commitment to that collaborative evaluation we talked about, the act of sharing and defending your limits with your peers, how does that impact the integrity of the T you finally set?
Are you setting a standard that is scientifically sound or just one that's convenient?
That's the question.
And that really is the essential challenge of quality control. Thank you for joining us on this deep dive into evidence-based decision-making. We hope you feel ready to tackle those 4 steps and apply that crucial Z factor on your next verification project.